So up until now, we've dealt with what's known as translational motion. And basically, in translational motion, we've been able to act like any object that we're talking about, that we can treat it as a point particle. Well, now what we're going to deal with is situations where we obviously can't treat something as a point particle. And the first example of that is when we have rotational motion. So if I've got a long rod here, and here's the center of the rod that I've got some pivot that the rod can spin around, well, clearly I can't act like this rod is just some point particle moving through space. So one of the things that we'll have to do here, and again this just sort of adds a layer of complication, is that you notice that I've drawn my rod in what we would traditionally call the X and Y axis, the XY plane, but it's rotating about an axis that points into and out of the page. So the axis that goes in and out of the page here, or in and out of the board, however we'll describe it, those mean the same thing. That axis is the axis that this rod is rotating about, and so that means that we really do have a third dimension here. So we'll often draw our stuff in the XY plane, but we'll need to be cognizant of the fact that it's rotating about. The axis of rotation is what we would often call the z-axis. So one of the things to sort of pay attention to is that rotational motion, sort of by definition, ends up where we're having to picture things three-dimensionally, because I'm drawing an object that's rotating in some plane, but I also care about the axis of rotation that points in the third dimension. So our problems, the upside of that for us, so the downside is that now we've got sort of a third dimension to deal with. The upside is that in some sense that third dimension is the only one that we're going to care about. So our rotational motion problems are going to end up being one-dimensional vector problems because all of those vector quantities that we're going to talk about lie along the axis of rotation. So even though we're going to need sort of three dimensions to picture what's going on here, we're going to be able to work it as a one-dimensional problem because all the vector quantities that we care about point along the axis of rotation. So that's just something to keep in mind. All right, so what are these quantities that we're going to care about? Well, for starters, and so what we're going to do here is again sort of highlight the fact that we talked about a set of quantities in translational motion. We're going to have an absolutely analogous set of quantities in rotational motion. Here's the quantity, position, in a one-dimensional problem where we happen to label that dimension the x dimension, and position is just basically saying what's the x value, right? And it had units of meters in SI units. Well, for rotational motion, we'll talk about the angular position. So from some point where we start counting the rotation, so in the same way that we would say, hey, from the origin here, there's some line that we'll start our rotation from. It'll often be the positive x-axis. And then we can measure the angular position using the angle theta. It has units of radians. So you're probably more used to thinking in terms of degrees as an angular unit. But the SI unit for our angular position is actually radians. Well, if you were interested in how the position changed, that was the displacement. And if you're interested in how the angular position changed, that's the angular displacement. So again, the angular displacement is just a way of saying final angular position, so theta final, minus initial angular position, so theta final minus theta initial, and again it has units of radians. If we were interested in how the position changed with respect to time translationally, that was kept track of with the velocity. So the velocity vector, again one-dimensionally, we were just interested in the x component. It had units of meters per second. And we could talk about the average velocity by taking the change in the x position divided by the change in time. So what was the average velocity between 2 points in time? Or we could talk about the instantaneous velocity by talking about, say, the initial velocity or the final velocity. We're going to be able to do exactly the same thing with angular velocity. So angular velocity keeps track of how the angular displacement as a function of time. So how does the angular position change as a function of time? We can keep track of the average angular velocity by the angular displacement divided by time. Or we can keep track of the instantaneous angular velocity by saying it has some initial angular velocity, some final angular velocity. And again, with a angle per time, the SI units for angular velocity are radians per second. Well, if you were interested in how the velocity changed with respect to time, that was the acceleration. Again, its x component, and it had units of meters per second squared. We could talk about the average, the x component of the average acceleration by saying what's the x component of the change in velocity. So how has the x component of the velocity vector changed between 2 points in time, and then divided by time. And then the instantaneous acceleration, for us, we just left as a constant value. So we said, hey, we're gonna work problems, we're gonna choose to work problems where the acceleration is constant. So our instantaneous acceleration won't change. We're going to do the same thing with the angular acceleration. So again, we can talk about the angular acceleration, its z component. So again, in all of this, we're assuming that the z-axis is the axis of rotation that whatever is rotating about. It's got units of radians per second squared. So again, angle per time squared. The average angular acceleration is nothing more than saying, well, what was the final angular velocity minus the initial angular velocity. And then again, we're going to divide by time. And then for the instantaneous angular acceleration, well, again, we're going to deal with angular accelerations that are constant. Okay? Another thing to highlight, x, v, a, these are all out of the Roman alphabet. Right? This is the alphabet that we're used to dealing with. Theta, this is a lowercase omega. This is a lowercase alpha. These are Greek letters. So rotational motion, one of the things that we're going to do when we're dealing with rotational things is that typically, not always, but typically, we'll use Greek letters to represent things that are going on rotationally to help signify that that's a rotational quantity that we're interested in. All right, so translational motion, we said, hey, there's a series of 3 equations. 2 of them have time in them. 1 of them is an equation that doesn't. But these were basically the 3 equations that we were able to use to work our kinematics problems to figure out how an object is moving, around. Well, we're going to have a set of 3 rotational motion equations, rotational kinematics equations, that will tell us about how an object is rotating. So notice that everything that was an x over here has become a theta over here. So instead of being x final equals x initial minus v initial t plus 1/2 at squared, this becomes theta final equals theta initial minus, my v has become an omega, t stays the same, my numbers stay the same, and my translational acceleration a has become a rotational acceleration alpha. So the x's become thetas, the v's become omegas, the a's become alphas, and I have exactly the same set of 3 equations. So I have 2 equations that depend on time, one that's going to tell me about final angular position, one that's going to tell me about final angular velocity, and then I have a omega squared equation, so an angular velocity squared equation, just like I had a velocity squared equation, v squared equation, that tells me about what's going on without time. Now, when was it that we could use this set of 3 equations? Well, we could use it whenever our acceleration value was constant. Well, when do you think we'll be able to use these rotational equations? We'll be able to do it whenever alpha, the rotational acceleration, is constant. So this is our set of 3 constant acceleration equations for translational motion. This is our set of 3 constant angular acceleration equations for rotational motion. And again, it's really going to be a one-dimensional vector problem. So all of these things, right, the angular displacement, the angular velocity, the angular acceleration, all of these things lie along the axis of rotation. So it's a one-dimensional vector problem, which means that the signs matter. And the convention we're going to almost always use is that counterclockwise rotations will get a positive sign, clockwise rotations will get a negative. Now again, this is just a common convention. If you choose to go the other way, that's fine, right? Choice of coordinate system is really up to you. This is simply the most common coordinate system that we'll use. But if you choose to let a counterclockwise rotation be negative and a clockwise rotation be positive, that's okay as long as you're consistent to your choice of signs. So just like any one-dimensional vector problem, once you pick a positive direction, in this case whether something is rotating clockwise or counterclockwise, you just need to be consistent to that choice.